Okay, so this is the second video on my channel regarding the University of Ibadan ODE Integration B. And in the last video, I did the problem 9, and this one is about problem 8. Right? If you want to check last video, just go to that playlist. Just search Ibadan ODE Integration B Methylasis World, and you might get that playlist. Right? Now let's get into this one. So this like seems to be a sum, right? And over here the n is going to infinity. In this sum, so it becomes an infinite sum because it's going from 1 to n, right? Over here, you might notice that over here you have I over n, right? Over here also you can just break this n square into one of the n's over here. You can take one of the n to over here, right? So in this sum, you basically have this expression of the form I over n. And when you see this, the Riemann sum should strike in your mind. Because I guess you know about Riemann sum, right? Riemann sum just says that, let's say if I have integration from a to b, f of x dx, this is same as sum from I equals to 1 to n of b minus a by n times f of a plus b minus a by n times I, right? So yeah, over here in this sum, basically you see this expression I over n, right? Over here, if you know about the how Riemann sum works, this is just a small delta element, and this is basically the f of f for the, like over here, let's say if I have a curve, I guess you know that, right? Let's say I'm going from a to b, so basically this is, let's say, some ai. So yeah, f of this ai basically gives this height, and this gives this small width, and that makes this small area, and we basically sum all of this rectangle from a to b, and that's how Riemann sum works, right? This is basically I by n times b minus a. Okay, now when there's I by n, then yeah, you have to get idea that basically we will be trying to convert a Riemann sum to the integral, right? And over here, let's say if I have a special integral where b is 1 and a is 0, in that case the integral becomes integral from 0 to 1 f of x dx, and this over here becomes I by n f of I by n, right? So sorry, not I by n, 1 by n, 1 by n f of I by n, right? But this is our delta x, and this is our like ith function. Okay, so yeah, now you see that this integral is in the form 1 by n f of I by n. Over here also, let's say if I have f of x is equals to x sine cube of pi by 4x, x sine cube pi by 4x. In this case, our f of I by n would just be that same thing, right? I by n sine cube of pi by 4 I by n, right? And also we have this 1 by n over here, and this can be taken out because the sum is in the world of n. This is same as 1 by n I equals to 1 to n f of I by n, right? And that's what we exactly have over here. This is just 1 by n sum of, this is just f of I by n, right? F of I by n. So yeah, so you see that that's the same thing actually. So this will just be integral from 0 to 1 of f of x dx, right? Okay, and now f of x in this case is x sine cube of pi by 4x. Now the only problem is how to evaluate this integral. So now that we have converted a sum to an integral, we are pretty sure that it's gonna be really easy, right? Okay, so now let's see how do we evaluate this integral. First of all, let's convert like sine cube, which is a 3 degree to 1 degree expression using some trigonometric formulas, that sine 3x is equals to 3 sine x, sorry, sine cube x is equals to 3 sine x minus sine 3x by 4. We will use this formula. This is because, I mean, we know that sine 3x is equals to 3 sine x minus 4 sine cube x, right? So if I use this formula, 4 sine cube x is equals to 3 sine x minus sine 3x, And yeah, this works. Okay, so let's use this formula. 0 to 1 x times 3 sine x minus sine 3x by 4, right? Okay, now this becomes, now uh, this will basically be 3 by 4 integral from 0 to 1 x sine pi by 4 x minus 1 by 4 integral from 0 to 1 x sine 3 pi by 4 x dx, right? Okay, so now this is just basic, this is just 3 by 4 I1 minus 1 by 4 I2, right? We need to evaluate these two integrals. To evaluate these two integrals, we will basically just evaluate another integral, which is 0 to 1. Let me not do it over here. We will need this space later on. Do it over here. We will evaluate another integral, which is 0 to 1 x sine ax. We will evaluate this general integral so that when a is pi by 4, we get the first one integral. When a is 3 pi by 4, we get the second integral, right? So let's evaluate this general integral so that we will reduce the burden of evaluating two integrals, right? Okay, so if for this one we just need to use integration by parts. So x, the integral of sine x is just minus cos ax by a, right? Minus cos, yeah, okay, yeah. And then we will have minus an integral from 0 to 1, derivative of x is 1, integral of sine x is minus cos ax by a dx, right? So now this is minus x cos ax by a plus, this is now just sine x by again a, so a square from 0 to 1, right? At 1, this is minus cos a by a plus sine a by a square. At 0, this is plus 0 because there's x, and here's again this is also 0, so minus 0. Okay, so we have the, so our answer is sine a minus a cos a by a square, right? Sine a minus a cos a divided by a square. Sine a minus a cos a by a square. Okay, so we know that's general answer, so let's try it substitute over here. So this will just be 3 by 4 sine pi by 4 minus pi by 4 cos pi by 4 by pi by 4 square, right? Minus 1 by 4 sine 3 pi by 4 minus 3 pi by 4 times cos 3 by 4 divided by 3 pi by 4 square, right? Okay, so now okay, again now let me take something common from both of them. Let me take this common, 1 by 4 times 4 by pi square. If I take this common, this will just be 3 sine pi by 4. Let me write the exact value. 3 by root 2 minus 3 pi by 4 root 2, right? And yeah, over here this is already taken common, so minus 1 by 9. This is 1 by root 2 minus 3 pi by 4, that's minus 1 by root 2, right? Okay, so this is 4 by pi square 3 by root 2 minus 3 pi by 4 root 2 minus 1 by 9 root 2. This is plus and again minus, so minus 3 pi by 36 root 2. Okay, now this is 4 by pi square. Let's take 36 root 2 common, I mean as LCM. So this is now 36 into 3, 30 into 3 90, 6 3 is 18, so 108 minus 9, so 9 times 4 is 36, so 27 pi 9 times 4 is 36, so 4, and then minus just 3 pi. So this is 4 pi square 104 minus 30 pi by 36 root 2, and this is 4 by pi square times, now oh, if I cancel with 4, 4 times 9 is 36, right? So this is just 1 by pi square, and then 104 minus 30 pi by 9 root 2. I can multiply numerator and denominator by root 2 just to rationalize. So that makes it root 2 by 9 pi square. So now over here it's a 2. You can divide the numerator, so 52 minus 15 pi. So that makes the answer. I also have the answer over here from the official um, organizers. Okay, so the answer is, yeah, answer is the same thing. Root 2 by 9 pi square, 52 minus 15 pi. Okay, now the elegance of the solution is like, how do you even wonder that in such sum you will eventually get root 2? Like that's so like absurd, right? You are randomly getting root 2 from nowhere. And also there's no any pi involved actually. Though inside it's an involved, but sign of the values with pi, they are never pi, right? From random values, if you make an infinite sum, you are getting pi and root 2. Like that feels so absurd to me, but yeah, I think this is the right answer if you do just numerical evaluation. So yeah, guys. So this definitely showed you how some infinite sum can be evaluated using the Riemann sum, and it's definitely helpful a lot of the time. So hope that was helpful. Thanks for watching. Do share with the friends and look forward to seeing you in the upcoming videos too.